they tell me from Rooted if you can get together a little bit, because there are people waiting, and apparently there cannot be people in the aisles, because if not, Kinepolis comes and puts us, logically a pure man, for the issue of the emergency door and so on. So if you can get together quietly and during the talk, I would appreciate it. We are going to continue with Marcos and Juan. I don't know whether to say things and turn red. I have known Juan for a long time. I am very fond of him. For me, he is on my list of exceptional professionals. And I have known Marcos for a little less time. They are going to talk to you about a subject that does a lot of very interesting research. I recommend you to follow everything they do at Carlos III, because every paper they publish is wonderful. I enjoy it a lot.
All yours.
All yours.
Well, thank you very much. Many thanks to RootedCon and CriptoRed for inviting us. I hope you like this research as much as we like doing it. You see, in a company, when they plan to make a defense against malware attacks, many times the worst situation that exists is that they get in. They encrypt your data, they exfiltrate it, and then you get this little screen, this little window saying, hey, you've been hacked. Now it's your turn to shut down. Well, but what if that little window didn't exist? What if, well, the purpose of malware is not to come in and say, hello, I'm here, but just to stay hidden, persistent, for as long as possible? Well, today we come to remind you that apart from ransomware, there is more malware out there, which is much more dangerous. Today we come to talk about rootkits, persistent malware, and with EO techniques. Concealment. Well, you have to know that historically there have been two techniques to create rootkits. On the one hand, we've had the user-level techniques. And basically, you pick a binary, you load a library, and from there you run code. And then we have the kernel-level techniques. Basically, you take a kernel module, load it into the kernel, and from there you have access to most of the system. Well, these techniques have a problem. On the one hand, the user-level techniques give you little access to the system and are very easy to detect. And then kernel-level techniques. Because if you are a malicious actor and you want to load a kernel module in a system, I can assure you that as I have an intrusion detection system, they will detect it because it is very noisy to load a kernel module. So what happens? We can understand that from an attacker's point of view, there is a need to find a new technique. A technique that offers us high access on the system once it is installed. That offers us stealth techniques, persistence techniques, and that is not very noisy when we are installing it. And well, since we are going to ask, well, hey, that not many people know this technique. The million-dollar question is there anything that meets all these requirements? And the answer is yes. It is called eBPF, and it is what we are going to talk about today. My name is Marcos Bajo. I am a security researcher in the COSEC group at the Carlos III University. And today I have come with Juan Tapiador, professor of security informatics, and also the principal investigator of the COSEC group. And, oh, sorry, I touched him by accident. And, well, together we come to tell you about this research that we developed last year, and let's see what we are going to learn today. First of all, Juan is going to tell us what eBPF is, how can you use it to program in eBPF, and what can we do with it. Then, we are going to explore what the offensive capabilities of eBPF are. I'll warn you that these are not vulnerabilities. That is, they are things that eBPF does not clearly tell you that you can do, but if you are a little bit smart and you find them, you can use them and use them in an offensive way. That is, to create malware. Then comes the fun part, because we are going to take these offensive capabilities and we are going to use them to create our own rootkit, which is called TripleCross. It is open source. You can download it yourselves. We will tell you the repository later so you can see how it works. And, well, if there is time later, because we only have half an hour, we are going to see a little bit. It is very good to put fear, isn't it? But let's see how you can defend yourselves against this kind of rootkits. Nothing. Without further ado, go ahead, Juan. He is going to tell you what eBPF is.
He's going to tell you what is. Hey, how are you doing? Hello, good afternoon, everybody. First of all, thank you for being here this afternoon. And secondly, forgive me because my voice is totally cracked today. I hope you can hear me perfectly. As Marcos said, before he presents the rootkit, we are going to talk about a couple of things, which is eBPF, for those of you who don't know this technology, and all the capabilities it offers for the development of offensive technologies. I will tell you a couple of them that are very interesting. Some of you probably know or are familiar with BPF, Berkeley packet filters, which is a very old technology that was invented in the 1990s, primarily to support user applications that do packet capturing or packet filtering tasks and needed capabilities that are not available, let's say, in user land. The most interesting thing about BPF is that it introduced a very nice architecture that consists of having a runtime inside the kernel, in which you can inject from user land some filters that are compiled and that allow you to determine, let's say, at runtime, the type of packages you are interested in or the processing you want to do with them. If you have used TCP dump or Wireshark ever, you will be familiar with this filter language. The idea internally is that the BPF runtime, what it does is to insert hooks that at the same time that the packets are passed to the protocol stack, they are also passed to this runtime so that you can do with them what you want, right? What is eBPF? The I stands for extended, and it's a technology that was introduced in the Linux kernel in 2014, which is still evolving. And what it does is it actually has little to do with BPF beyond the name. What it does is it takes that same idea and extends it to give much, much more observability within the kernel. Not just, say, to network events like a packet arriving or a packet leaving, but pretty much anything that happens inside the kernel, pretty much anything. In fact, they have access to, from eBPF, you have access to events that are not available even to, let's say, loadable kernel modules. And in addition, they have a very interesting feature, and that is that they allow you to maintain state inside in the form of some data structures that allow you to communicate with username, as we will see now. One way to define what eBPF is to see it on the one hand as a programming language. I was going to say standard, but it's not standard because it's a very limited language. It is a little bit like C, but there are things you cannot do when you make a program in eBPF. For example, until recently, you could not do loops because, as we will see now, it has a verifier that has to be able to determine if the program is going to finish. This is a problem, let's say, a bit difficult in computer science. And one way to bound that problem is to not allow loops, and so the program terminates at the end. And on the other hand, it is a runtime. This runtime is the more sophisticated one that I was saying before, which extends this idea of having something inside the kernel. And the idea is that when you compile a program in eBPF and we produce this bytecode, that bytecode from user land can be injected into the kernel, it goes through a verifier. What this verifier does is it determines that it's correct, that the program is going to finish, and once it is approved, depending on the configuration that you have in the kernel, it is going to be compiled to just in time. Or it's going to be put into a virtual machine that's going to be interpreted. This is up to the system operator to decide. Once this has happened, either one of the two things, we have a program that is already loaded, and what it has established is a series of events that are of interest to it. When these events happen, well, the Linux kernel is going to transfer control to it. You can see it as a system, let's say, of hooking, only a little bit special. What things can you do from there? Well, you have access to a lot of internal kernel structures, to kernel probes, to user probes, to trace points, to XDP, and also to what are called BPF helpers, which is a way to call normal functions of the app in Linux without having to call them directly. One of the most interesting things that eBPF introduced later on is this idea that a program is not only, let's say, what's going to be injected into the kernel, but it also has a part that lives in userland and is able to communicate with its twin that's inside the kernel through BPF maps, which are essentially a data structure where you can store state, where you can store content and bring it up into userland or bring it back down, right? Here you can see a code example so that it's not all boxes and arrows, and you can see what we're talking about. There you can see, for example, how the interest is declared in a system call, which is open at and the hook that we put to take the control when that event happens, okay? And how the data is passed from one side to the other. In the last line of the program on the left-hand side here, you can see, for example, how you can store the name of the file that has been opened in a map, and essentially you can do pretty much anything you want by working with the events that happen inside the kernel. A very interesting part of eBPF is the networking part, of course. And in addition, eBPF introduces a concept that is the XDP program concept, which is of absolutely brutal interest for the development of offensive capabilities. When you create an XDP program and inject it into the kernel, this program receives packets from the network card through the driver before they reach the Linux kernel itself. So that allows you to mishandle them and manipulate them by waiting for the observability that the kernel is going to have of that packet, right? So you can do some really nice things with that. In addition, you can also generate the typical input and output filters, so to drop packets or to modify them on output and so on. But in particular, this primitive is very interesting. It has only one limitation, and that is that you can read, modify, discard packets, but you cannot inject packets. If you want to manipulate traffic, you have to live with the traffic that already exists. XDP programs are extraordinarily simple, just like any eBPF program. They are declared as such and have a number of peculiarities. If you feel like learning how to program this, you will see that there are things like safety issues, especially determining that you never go outside the thresholds of the buzzer that it has received, and doing all the parsing of the headers, of the link layer, of the IP layer, of the TCP layer, that you have to be, let's say, careful of that, because the packet has not yet been parsed by the kernel, right? Where is eBPF today? Well, it's in almost every major cloud provider. They have adopted it for monitoring tasks, some of them, for security, and above all for profiling. Because being able to inject, let's say, custom elements into the kernels allows you to make very fine measurements of where resources are going, how many cycles each program is consuming, where the bottlenecks are, and so on. And there is a whole field of study of profiling using eBPF that is very interesting right now. Windows introduced it very recently, although the version of eBPF for Windows is still very limited, and Android also introduced it a couple of years ago, and you can find it already in there. For those of you who are familiar, for example, with the world of rootkits, you will understand the parallelism between the standard capabilities it had, the access to the kernel APIs, and what this offers, right? Anyway, I'm going to tell you about a couple of offensive capabilities that are very interesting. Of all the ones we implemented in Triple Cross, there are two that are very nice and that I wanted to tell you about so that you can better understand what Marcos is going to tell you. One is the possibility of having some read and scan primitives and arbitrary writes in the memory space of a process. This is the typical memory map of when a process is loaded, where you can find the instruction pointer and the current stack frame, right? Well, with the local variables and the return address and all these things that, you know, right? The interesting thing is that when you inject an eBPF program that's interested in hooking a system call that a process issues, among the arguments that are passed to the eBPF program, you have the ability to go outside of those bounds and write left or right, and also scan the stack. This is very interesting. For example, in this diagram that you have here, you can see how a system call, which in this case is to open a file, ends up in your eBPF program and in your eBPF program, which is that you have declared a trace point. You can access the file, which is a pointer. It is a pointer that is stored in the corresponding stack frame, and playing with these offsets and knowing the types, we are going to be able to overwrite the stack of the stack frame of the program. The stack of the stack frame of the user program back and forth, and also scan it. Okay? This is very interesting because this is the foundation for being able to exploit programs and do things like dynamically inject libraries or alter your code in execution type. It's really very powerful stuff. Another thing that is very interesting for us as an offensive capability is the XDP programs that I was talking about 5 minutes ago, right? I was telling you XDP programs are interesting because they are the ones that are able to capture traffic before it gets to the kernel, right? What is that good for? Well, it's good for a lot of things. For example, you can make a packet that a device on the perimeter of a network has monitored with certain characteristics. You rewrite it and you get what the kernel observes to be different from what has been observed on the network, right? Which has a lot of applications. One of the things that we've used it for is to set up a command and control channel without broadcasting packets. But directly what we do is when an application from the host that's infected launches a request, for example, standard HTTP, you can capture, subscribe to this event, capture it, modify the packet, and redirect it to a different IP and to a different port, right? When this comes here, you set up your standard communication, and when the timer goes off that the packet hasn't gone out, the second one is regenerated, the second one you leave it. In this way, for every packet that the infected machine generates, you have the possibility of generating two, one for you and another one that you let pass as if nothing happened, right? This is interesting because you can ride on top of the telemetry of the system or many applications that are continuously generating traffic, and you can have the possibility to establish command and control channels that are not observable inside the kernel, let's say, because there is no application that is generating that traffic, right? With that, I'll give the floor back to Marcos, who is going to show you how to use some of these things in the triple cross design.
Well, thank you very much,
Marco
Juan. I hope that
Antonio
these primitives
Lozano.
are clear to you, because now
Thank
we
you,
are going
Juan.
to use them, and we
I
are going
hope
to
you are
use them
clear
to build
about
all
these
the modules
primitives,
of our
because now we are
rootkit.
going to
I have to
use
tell
them,
you, this
and we are
figure is
going to
here to
use them
impress.
to build all the
Okay?
modules of
But
our
let's say
rootkit.
this triple
I
cross
have
is
to tell
composed
you,
of several
this figure
modules.
is to
Each one
impress,
does one
okay?
thing. We have a
But
persistence
let's say
module,
that this
a
triple cross
membrane
is
injection
composed of
module, a
several
stealth
modules.
module, many
Each
modules.
one does one thing.
So,
We have a
what we are
persistence
going to do
module,
is,
a
we are
membrane
going to see
injection
some of
module,
them,
a stealth
the ones we
module,
have time for,
many modules.
and others, maybe
So
we will see them
what
a
we are
little
going
bit
to do
faster.
is,
Mention that this is
we
the
are going to see
repository of
some
the
of them, the ones we
rootkit.
have
You can
time
access
for,
and look at everything it can
others.
do. So if anything
Well,
is not
maybe
clear
we
to
will see
you or
them
you
a
want
little
more
bit faster.
information, then
Mention that this is
access
the
it and see it.
repository of the rootkit.
Okay, so let's go to the
You can
first module.
access and look at
The objective
everything
of
it
this
can do.
module is that we want to
So,
take any
if
process in the
anything is
system
not
and we
clear
want to
to
make
you
it
or you
execute the
want more
code that we want.
information,
Okay?
well,
So
access it,
we're going to take, for
see it.
example, a process that's
Well
already
then,
running, like
let's go with the
systemd.
first module.
We're going to force
The
it to load a
objective
library.
of this
We're
module
going to
is
make
that
it
we
run,
want to take
and then we're going to
any
make sure that it
process
keeps
in the
running in the
system
process.
and we want to make it
Okay?
execute
That
the
it
code
doesn't
that we
crash
want.
system.
Okay?
How do we do this?
So
Well, so we have to
we're
go a
going
little
to
bit
take,
to the
for
basics.
example, a process that's
Okay?
already
We
running,
need to
like
explain lazy
systemd.
binding.
We're going
What
to
you
force
need
it
to
to
know
load a
basically
library.
is
We're
that
going
when
to
you
make
want
it
to
run,
execute
and
a
then we're
system
going to
call
make
in a
sure that it
process,
keeps
you
running
don't
in the
do it
process,
directly from the
okay?
text section
That
to the
it doesn't
kernel,
crash
but in
system.
fact that
How do
system
we do
call,
this?
that instruction,
Well,
is
we have to go a little
encapsulated
bit
in a
to the
library
basics,
such as
okay?
libc.
We need
So
to
you have to
explain
jump to the library
lazy
from the
binding.
text section, but you can't
What
jump
you
to
need
it
to know
because the
basically
library
is
is
that
loaded dynamically.
when you want to
So
execute a
when you run the
system call in
program,
a
you don't know
process,
where it is.
you don't
So
do it
what do you
directly
do?
from the text
Well,
section to the
in the
kernel,
ELFs,
but
in
fact
the
that
Linux
system
systems,
call,
you
that
have an additional
instruction
section called the
is
GOT,
encapsulated
which is
in
going
a
to do that
library
when you
such
run the
as
program,
libc.
or,
So
well, also
you have
depending
to
on the
jump to the
configuration,
library from the
when the
text
first time the
section,
system
but you
call is
can't jump to
executed,
it because
the
the
linker will
library is
go and
loaded
write there the
dynamically.
address to which you have to
So
jump in
when you
libc.
run the program,
And
you
then
don't
the
know
text
where it
section
is.
will jump to an
So what do
additional
you
section
do?
called the
Well, in the
PLT.
ELFs,
That
in the
using that
Linux
address
systems,
that
you
is in
have
the
an
GOT,
additional section
it
called
finds
the GOT,
then the
which is
address to
going to
jump
do
to
is
in
that
libc.
when you run
So
the
we jump
program
from the text
or,
section to PLT,
well, also
using the
depending
address
on
from the GOT
configuration,
to the
when
library,
first time you
and
run
from the
system
library to
call,
the kernel.
the linker
And then,
is going to go
well,
and
we
write
just go
there
back
the
using
address to
return
which you have to
instructions.
jump in
Well, our
LABC,
challenge is to embed in this
and then
architecture
the
a
text
malicious
section will jump
library.
to an additional
How are we
section
going to
called
do
the
this?
PLT
Well, very simple.
that
We're going to
using that
modify the
address that
GOT.
is in the GOT,
We're going to
it
make it so
finds
that instead
then
of referencing the
address
address
to
of the
jump to
libc
in
library,
LABC.
it references
So
our own
we jump from
malicious
the
library.
text section to PLT
So you jump from the
using
text
the
section,
address
go to
from
the
the GOT to
PLT.
the
The
library, and
PLT
from
will
the
use the
library
wrong
to the
address
kernel.
of the GOT that
And
we have
then,
modified.
well, we
We
just
will
go
jump
back
to our
using
malicious
return
library,
instructions.
execute all
Well,
the
our
code,
challenge
jump
is
to
to
the
embed
original
in this
library, and
architecture
from there we go to
a
the kernel.
malicious library.
As you can see,
How
we
are we
get to
gonna
the
do
kernel,
this?
but this time we
Well,
execute our
very
code.
simple.
Well, in
We
a
are
real
going to
example, this
modify the
gets more
GOT.
complicated
We are
because we
going
have
to
to
make
do
that
many more
instead
things.
of referencing the address
Basically,
of
we are
the
going to have a
IDC
program, a
library,
tracebook,
referenced
which is
in
going
our
to do a
own
hooking to a
malicious
syscon,
library.
such
So
as
you jump
opening
from
a
the
file.
text section,
This is
go to the
implemented, by the
PLT,
way, in
and
our
the
root.
PLT will use
So
the
what
wrong
we're going to
address
do
of the
first
GOT
is we're
that we
going
have
to use the
modified.
tracebook to
Let's
take
jump
the
to our
argument that
malicious
we've been
library,
passed,
run all the
which
code,
remember
jump to
is a
the
pointer to
original
the stack.
library,
When we're in
and
a
from
stack,
there
we're
go
going
to
to
the
do a
kernel.
memory scan.
As you can
We're
see,
going
we
to go
still get
forward
the
until we
kernel,
find the
but this time
library.
we execute
When
our
we're in the
code.
library, we're going to
Well, in a
locate
real
certain
example,
functions
this
that
gets
are
more
clave that we
complicated
need to
because we
load
have
the
to do many
library
more
and then
things.
execute it.
Basically,
Why? Because,
we're
well,
going
we
to
have
have a
ASLR, CLR. So we need to find the functions first so that we can then use them in
like
our
you
set
can
code.
open a file.
Because yes, we have a set
This is
code that's in
implemented,
charge
by
of
the
loading
way,
the
in our
library and
toolkit.
executing it.
So what we're
We
going
are
to
going
do
to put it
first
in a
is we're going to
section
use
that is
torch
marked
Pong
as
to
executable,
take the
and
argument
we are going to
that,
modify the
we've been
GOT
passed,
so that the
which, remember,
syscon,
is a
the
pointer to
address that is
stack.
in the
When
GOT
we're in the
that
stack, we're
references
going
the
to do a memory
syscon
scan.
is
We're
going to
go
jump to the
forward
set
until
code,
we find
which
the
is going to be in
library.
charge of
When
loading
we're
the
in
library.
we're going to
You go to the
locate
malicious
certain functions
library,
that are key,
you
that we need
execute
to
the
load
code,
library
and you
first
go back to
then
the
run
set
it.
code that is
Why?
going to be in
Because,
charge of putting all the
well, we
variables
have
and
the
all the
CLR,
stack
so
in
we need to
place
find the
so that the
functions
process
first so
doesn't
that we can
cache.
then use them in
With
our
this,
set
we have
code,
executed
because, yes,
malicious
we have
code.
a set code that's responsible
Well,
for loading
what would a
library
rootkit
and
be if
execute.
it did not also have
We
a
are going
CDOS?
to
Well,
put
of
it
course,
in
ours does too.
a section
I would like to tell you that
is
our
marked
CDOS has a
as
lot of
executable,
functionalities. We have a lot of
and we are
cells.
going to modify the GOT
You can
so
execute
that
commands, filter
the
information,
syscall, the
but we
address
are going
that
to
is in
focus
the
on
GOT
several of
that
the
references
modules.
the syscall
First of all,
is going to
the
jump
first
to
thing
the
you
set
need to
code
know
that
is that
going
we
to
have a
be in
client that
charge
you can
of
install
loading
on
the
your own
library.
machine,
You go
with
to
which
the
you can
malicious
remotely control the
library,
rootkit
run the
that is going to
condo,
be
and
installed
go
on
back
another
to the
machine
set
that has
code
infected
that
it.
is going to be
So,
in
I am
charge
going
of
to
putting
explain
all the
first how you
variables
can
and the whole
execute
stack
commands with our
so that
client
the
on the
process
infected
doesn't
machine.
crash.
The first
With
thing
this,
you need
we
to
have
know is that
executed
when you make
malicious
the
code.
request to execute a command from the
what
machine,
would a rootkit
from the
be
client,
if it
from
did
your
not also
attacking
have a C++?
machine, it will send what we
Well,
call a
of course,
trigger.
ours also
A
has
trigger
it.
is nothing
I
more
would
than a
like to tell
packet or
you
a
that
series
our
of packets that we
C++ has
have
a lot of
prepared
functionalities.
specifically to bypass
We have
any
a lot of
traffic
salts.
analysis system
You can
or
execute
firewall that
commands,
is looking at the
write
traffic.
information.
So, for example,
but we
this
are
is one
going
that
to
we
focus
have,
on
but we
several
have
of the
more.
modules.
We have put
First
our
of all, the
payload
first thing we
inside
have
the
is that
TCP headers,
we have a
which
client
is
that you
also
can install
encrypted,
on your own
and our
machine,
payload is also
with
going
which
to
you
tell
can
you the
remotely
address where the
control the
attacker
rootkit
is,
that is going
so
to
that
be
you can
installed
send
on
the
another
traffic
machine
again.
that has
And we have
infected it.
also included
So
the command that
I'm
we
going to
have
explain
requested,
first
which in
how
this
you can
case is
execute
that we have
commands with our
established a
client
cell.
on the infected.
Well,
As I said, we are going
The
to have
first
a
thing you need to
program
know
in the
is that when
rootkit,
you
which
make
is
the request
XDP,
to
which is going
execute
to
a
take
command
this
from the
trigger,
machine,
it is going to
from
hide
the
it from
client
the
of your
kernel by
attacking
dropping it,
machine,
and it
will
is going
send
to
what we
unpack
call
the
a
payload.
trigger.
It is
A
going to
trigger
check
is
that
nothing
we are
more than a
indeed setting
packet
up a
or
cell,
series of packets that we have prepared specifically to bypass any traffic
and a
analysis
program that
system
is
or
at user
firewall
level,
that
which
is
also
looking at
belongs to the
traffic.
rootkit, will
So,
establish a
for
cell,
example, this
and
is one
that's
that
it.
we have, but we have more.
Now you will say, but why do we have a
We have put our
rootkit that is at
payload
kernel level,
inside
and then we
the
establish a cell
TCP
at user
headers,
level?
which is also
What's the point
encrypted,
of generating
and our
packages at
payload
user
is
level
also
with a
going to tell
rootkit
you
at
the
kernel
address
level? I don't
where
know.
the attacker
So we
is,
thought about
so
doing
that you
another
can
cell,
send
which we
the
call the
traffic back
phantom
to
cell,
him.
which is basically the
And
same thing.
we have
But
also
we're not going to
included the
generate a
command
single
that we
user
have
level package.
requested,
It's all
which in
done
this
at the
case is
kernel
that we
level.
have established
So
a
what we're
cell.
going to do
Well, as I
is
say,
we send the trigger,
then
the
we are going to
XDP
have
is
a
going to grab the
program
payload,
in the
our
rootkit
trigger,
that
it's
is
going to extract the
XDP,
payload, and it's going to
that is
say,
going to take
okay,
this trigger,
we need to set up
it
a
is going
phantom
to
cell.
hide it to
And
the
now we're going to
kernel,
wait.
doing
We're
a
going to wait
dropping,
for
and it
whatever
is going to
program
now
is on
unpack
the
the
infected
payload.
machine
It
to
is going to
generate
check
traffic.
that we are
For
indeed
example,
asking
you
to
have a
establish
browser
cell,
that's going to try
and
to
the
access a
program
server
that
that's
is at
somewhere.
user level that
So,
also belongs
when
to
that
the
packet is
rootkit,
generated,
it is
we're
going
going
to
to take
establish
it
a
with a
cell,
TCGRES
and
program,
that's it.
we're going to modify it,
Well, now
we're
you
going to
will
modify
say,
the destination
but why
IP,
do we have a
we're going to
rootkit
send
that
it
is
to the
at kernel
attacker,
level,
and
then
we're
we
going to say,
establish a
hey,
cell at
we're
user
ready to
level?
set up
I
our
mean,
phantom
what's the
cell.
point of generating
And then the
packages
original
at
packet
user
will
level
already be
with
sent
a
after the
rootkit at
TCP
kernel level?
retransmission.
I
At
don't
that
know.
point, we're going to
So
see in the
we
demo,
thought about
it's
doing
going to
another
open up a
cell
cell,
that
and
we
it's going
call
to
the
say,
phantom
hey,
cell,
enter the command.
which is basically the
We
same
put
thing,
in,
but we're not going to
for
generate
example,
a
the
single
command
user-level
WAMI.
package.
It sends it to
Everything
the
is done
XDP
at
program.
kernel level.
We take it,
So,
we run it at the
what we're
user
gonna do
level,
is we
because
send the
obviously you
trigger,
can't do
the
that in the
XDP is
kernel.
going to take the
We
payload,
pass the response
our
to another
trigger
program,
is going to
TCGRES.
extract the
We
payload,
wait for more
and it's going
traffic,
to say, okay,
another
we need to
packet,
set up a
another
phantom
reply
cell.
to another
And
server.
now we're
We
going to
modify
wait.
it and we send
We're
the
going to
response.
wait
We say,
for
hey, we are
whatever
root.
program is
And
on
that's
the
it. That's how it
infected
works.
machine
Very
to
quickly,
generate
two other
traffic.
modules.
For
We're going to
example,
see
you
how
have
to
a
run
browser
programs from
that's
the
gonna
kernel
try to
and also how to
access a
escalate
server
privileges.
that's somewhere.
Okay,
Well,
so what you need
when
to
that
know
packet
is that
generated, we're
eBPF
going to
cannot
take
run
it with a
programs from the
TCGRES
kernel.
program.
It's just a
We're going to
limitation.
modify
You
it.
can't.
We're going to modify
So
the
what we thought
destination
is,
IP.
well,
We're
will there
going to
be
send
any
it to the
programs out
attacker,
there that
and
will
we're going to
run
say,
the
hey,
syscall
we're
to run a
ready to set up
program,
our
which is
phantom cell.
sysexe.v?
And then the
Well, we
original
said, well,
packet,
what if we
well, it will be
modify the
sent
name of the
after the
syscall, the
TCP
name of the
retransmission,
argument
right?
that's stuffed into
Well,
the
at that
syscall,
point,
so
we're
that
going to see
instead of
in the demo, it's going
that
to open a
original
cell,
program that
and
was
it's going to say,
originally
hey,
us to run.
enter the command.
Did we run our own
We
program?
enter, for
Well,
example,
that's
the
what we did. A
command,
malicious
who am
program
I?
is executed.
It sends it to the XTP
You'll say, well, but then
program,
the
we
user
take
has
it, we
executed,
send it, we
he wants to execute
execute
a
it at
program
user
and it
level,
executes another one. He's
because
going to
obviously
notice,
that
isn't
can't
he?
be done in the
Well,
kernel.
no, because we are
We
going to
pass
put the name of the
response
original
to
program in the
another
arguments of the
TC
syscall that
program.
executes the
We wait
malicious
for more
program,
traffic,
so that
another
the malicious
packet,
program
another
is ready to
response to
extract the
another
name of
server.
the original
We
program,
modify
and then
and we
executes
send the
another
response.
syscall
We
with
say,
the
hey,
original
we are
program,
root, and that's
and
it.
then executes
Well,
another
that's how it
syscall with the
works.
original
Well,
program.
very quickly, another
The
two
original
modules,
program.
okay?
And that's it. Two
Let's see
programs
how
are
to run
executed.
programs from the kernel,
Well, very quickly,
and
it is the
also how
scale
to
of
escalate
privileges that you know that
Okay,
when
so
sudo wants to have
what you need
privileges
to
and
know is
execute
that
sudo,
eBPF
it
cannot run
accesses the
programs
file
from
of
the kernel.
sudoers.
It's just a limitation. You can't.
This is the
So what
file
we
that
thought
tells you
is,
what
well, will
permissions
there be a
each
program
user
out
has,
there that will
etc.
run the syscall to run a program
Well, so
that
what
is
we do is, when
sysexec.b?
any program
Well,
that
we
the
said, well,
rootkit
what if we
wants
modify
to
the
have
name
privileges
of the
accesses the
syscall,
sudoers file,
the name
we
of the
modify
argument that's stuck in
everything
the
that reads
syscall,
from the
so
sudoers
that
file
instead
with
of
that, which means this
original
program has
program
all the
that's
permissions it
originally had to
wants,
run,
and apart
we run
from
our
that,
own
without a
program. Well,
password,
that's what
you
we
just
did.
have them. and that's it.
malicious
And then you'll say,
program,
well, and all that,
is executed,
those
you
brackets
will
that
say,
are,
well, but
well,
then the
that's
user
because
has
we want to
executed,
comment out all
he
the other
wants to
data,
execute a
okay?
program,
Because if we
and
don't,
another one
it
is
blows up.
executed, he is gonna
That's it.
notice,
Let's go
right?
to the demo.
Well,
It's
no,
going to be
because
very
we are
quick. It's
going
2
to
minutes.
put the name
Well,
of
the
the
first demo
program
is
in
the
the
phantom cell
arguments
that
of
I
the
have told you.
syscall
On
that
the left, you
executes
have
the
the
malicious
attacking
program,
machine, the red one,
so that
and on the
a
right, you have
malicious
the
program
machine
is
that
ready
is
to
infected with
extract
the
the name of
rootkit.
the original
I remind you
program
that the
and
phantom
then
cell consists of
executes another
executing a
syscall
command,
now, yes,
but
with the
without having
original
to
program.
generate any
And
package
that's
at the
it, two
user level.
programs are
So
executed.
we're going to
Well,
install
very
the
quickly, it's
rootkit on the
privilege
right-hand side,
escalation.
and we're going to
You
use
know,
our client, our
when
rootkit client on
sudo
the right-hand
wants-
side. We're
when
going to set
program
up a
wants to have
phantom shell
privileges and run sudo
with
it
the
accesses
IP of the
sudo
machine
file. This is
that's
the file
infected
that
with the
says
rootkit.
that
And as
each
you can see,
user-
we don't do any response or
privilege
anything,
each
so it's
user
waiting.
has,
What is it waiting
if they
for?
need a
For us to
password and
generate
so on.
traffic. So what we're going to do,
Okay,
we're going to
so
go to the root
the
page.
machine that has
We generate
privileges,
traffic
let's
by
see, I'm gonna
accessing the
make a
root
little
page.
mistake with
And
that
now, yes, as you
permission,
see down there,
right?
it's
You've got them.
received.
And,
a command line appears
the
where we
first
can enter
mistake
the
is
command
the
that we
first
want.
user, no,
We are
no,
going to
no,
enter,
no,
for
no,
example,
no,
John,
no,
we
no,
send
no,
it,
no,
and
no,
we don't
no,
get a
no,
response.
no, no, no,
Why?
no, no, no,
Because
no,
there
no,
is no
no,
traffic
no,
yet.
no, no, no,
So
no, no, no,
we are
no,
going
no,
to
no,
access
because
again
it's
to the
beta.
root page.
I've
We
had
generate
enough.
traffic.
I've had enough.
The
It's
answer is
2
sent
minutes.
again.
Okay,
And as you can see,
I
we are
gave it
root.
up. Now I'm attacked by the ROC and the ROC. Well, this one's short too, okay? Okay. Let's see how to inject the library. Okay.
Well, this is a short one
So,
too, okay? Let's
we
see
have
how
a
to inject the
program that
library.
I've prepared,
So we have a
okay?
program that I've prepared called
It's called
Simple
Simple
Open.
Open.
This is the
This
rootkit
is the
configuration.
rootkit
I'm going to
configuration.
tell it to inject the
I'm
library
going
into
to
this
tell
program.
it to inject
So
the
it's a very
library
simple program.
into this
I
program.
mean, it runs a syscall
okay?
of opening a file once
So
and
it's
then
a
again.
very simple
That's it.
I mean,
So
it
what
runs
we're
a
going to do
syscall
is the first
to
time it
open a
runs,
file
we're
once
going to
and then
modify the
again.
GOT.
That's
And the
it,
second
that's
time
it,
it
that's
runs,
it.
it's
So
going
what
to
we're
run
going
our
to do
malicious
is
library.
The first time it runs,
So we're going to
we're
go
going to
one more
modify the
time.
GOT,
Oh,
and the
okay,
second
one
time
important
it
thing.
runs,
The
it's going to
library
run
that we're
again.
going to load,
That's our
I've
malicious
preloaded it
library,
so that it
okay?
sets up a reversal
So
with
we're
the
going to
attacking
go one
machine.
more time.
Okay? So
one
when we run the
important thing,
library, it's
the
going to
library
open a
that we
connection
are
to the
going to
machine,
load, I've
the red cell.
preloaded it so that it
So
sets
while we
up a
install the
reversal
rootkit,
with
we're
the
going to go
attacking
run the
machine,
program.
Okay, so when we run the library, it's going to open a
And when we
connection
run the
to
program,
machine, the red
we're
cell.
going to see
So
that we're going
while
to
we
get a
install the
message that
rootkit,
says,
we're going
hey,
to go
the
run
library has been
program.
injected,
And when we run
and
the
we're going to
program,
get a
we're going to
connection.
see that we're going to get a message that says,
There
hey,
it is.
the library has been injected, and
That's
we're going
it?
to get a connection. Thank you. Leave me.
Oh, well, one thing. We have more demos in the repository. So if you access the repository, we have more demos there if you want to see it, okay? And, well, we're going to pass this around, but we have more modules, okay? If you want to take a look at it, we've got persistence and we've got stealth as well. That's it.
Thank you,
Go ahead,
Juan. Thank you, Marcos. Well, as you can see, we ended up a little bit out of time. Our idea with Triple Cross was to do an exploration of offensive capabilities. And in the end, we ended up integrating the 4 or 5 that are perhaps the most striking. But there's a whole development behind other very cool command and control channels and other techniques that can be used that are very interesting. I'm going to take one more minute to conclude this talk by giving you a glimpse of what can be done. Rootkits in general, and eBPF-based ones are no exception, are in general super noisy, and detecting them is usually not a big problem. What can be used? Well, the standard EDR techniques or network appliances. There are some things that are going to cost you, but others that are perfectly possible. For eBPF-specific defense techniques, several have started to emerge. The first are monitoring. It would be the equivalent of an EDR, but for eBPF. What they do is monitor the activity of the eBPF system call and take its arguments, and using standard techniques of signatures, rules, etc., try to detect what is going on. There are also systems to allow only signed eBPF programs to be loaded, but that is kicking the problem down the road and passing the problem on to someone else. You can do eBPF installations that are a little safer and have fewer capabilities if in an environment that you are in, you are not going to run arbitrary programs, but only a few, and you can afford that. And of course, you can have kernel lockdown, integrity, confidentiality techniques. If by default, if you can't alter the kernel, you can't do any of this at all. But not every organization can live in that standard, okay? If you're interested in this topic, we've left here some links to at least 3 implants discovered in the wild in the last couple of years that make use of eBPF, which are BVP47, BBP-DOR, and Symbiote, which all 3 use techniques, well, let's say, equivalent to some of the ones that we've presented here and some different ones. And there are also a couple of very nice talks at DEF CON that talk about offensive eBPF capabilities for packet manipulation and for kernel access, etc., which I recommend you watch if you like this topic. That's all. Sorry for the excess of time, and we leave here again the link in case someone wants to take a look at the code. Thank you.
We are running out of time, but 2 quick questions. Download.
I see a hand there.
If you can, we'll save time. Those
Is
of
it
you
in
in
the
the room,
room?
please get together. There are a lot of people waiting to turn in, so there's more room.
Nothing, I just wanted to ask you if there is a dynamic scanner, let's say, a Kubernetes type container orchestration environment. I know there is one called Falco, but I don't know if you know any better than this one.
No, I'm not very familiar with.
I know Falco works with eBPF, but
Yes.
I tried it very little at the moment.
Almost all the hypervisor level cloud monitoring techniques have moved to eBPF in the last few years because it allows you to do things that you can't do otherwise. But I can't tell you which one is better or how, what capabilities it has versus another product because I don't know. I'm sorry.
One last question.
Well,
Hey, what's up?
first of all, thank you very much for the talk. It amazes me to see this open source. This is worth a lot of money for many people, so congratulations for that. One question, just a curiosity, is why do a privilege elevation? And I guess to install this in the kernel, you are already root. So what's the point of making a privesc module?
Okay, first of all, simply because we can. I mean, we've done
You've
it
done
because
it
we
just
can.
because.
But secondly, I mean, if we have persistence, then, well, it's interesting to keep those privileges. So we have privilege escalation in runtime. I mean, if we want to run any program at user level, then we would like it to run at root level. And then one that we have not had time to present it, but well, we can also maintain the privileges, let's say after the reboot. That is, the rootkit maintains the privileges as well. So it is simply to fulfill us. Come on, to have it.
And also to elevate the privileges to another process so that eventually you can have different modules at different levels, and not to you, but to another process that you have deployed in your implant that you want to temporarily elevate the privileges. And it's an interesting primitive in general. Thank you very much. Thank you very much.
Ole, radio for who and shell for whom? Marcos.
Marcos, the first, the second, that is the radio for the second and the shell for the first.
Well, you can come by later. A big hug.
Nothing, thank you very much.
Thank you very much.